everyone, welcome to today's video on solving systems of equations using the substitution method. So last week we looked at solving systems of equations graphically, where we graph both of the linear equations and see where the lines intersect, and that is the solution. This week we're going to look at how we can do it without graphing, just using algebra. And we're going to be using this concept of substitution, which you've done a lot with before, just not exactly in this concept. But we know the idea of if we get the solution x equals 2, we can substitute 2 back into the original equation, replace the variable x with 2, and then evaluate and see what happens. So we're going to use the same sort of logic to solve these systems of equations. These problems can take a good amount of time. There's a lot of steps involved. So the general kind of process we're going to take is we want to make sure that one of the two equations has a variable solved for, meaning a variable is by itself. So like y equals something, x equals something, a equals something. Okay, because then that's going to allow us to substitute what that variable is equal to into the other equation for the variable, which we'll see lots of examples for. We then get a one variable equation which we can solve. We can figure out what one of the variables is equal to and then substitute it in to find the other variable. Okay, as always, when we're solving systems of equations, we are looking for the x value and y value that will make both equations true at that same point. Okay. As with, of course, systems of equations with graphing, systems of equations can have one solution, no solutions, or infinitely many solutions. And it's going to be one solution if we get some x, y value. It's going to be no solutions if we get to some false equation, something like 2 equals -4, and then it's going to be infinite solutions if we figure out that both of the equations are actually the exact same thing, and we might end up with some true statement while we're solving, like 2 equals 2, which is always true no matter what. So in example 1, we're going to solve this system of equations algebraically using the substitution method. If you watched my previous video about solving systems using graphing, then we've actually seen and solved the same problem before. This graph has the two lines graphed, and we can see the solution is 2, 2. That's great whenever they give us the graph, but without that it's a little bit annoying to actually create a graph. So in this, we're going to talk about how we could solve this without needing to graph it. In this situation, this is somewhat of a special situation in the realm of substitution. We have two variables that are already solved for. So we have that y is equal to 3x minus 4, right? And then we have that y is equal to -1/2 x plus 3. We are trying to find the x and y pair, the x and y value, that make both of these equations true at the same time. So if it's true that y equals 3x minus 4 and y equals -1/2 plus 3, and we're trying to find that x and y value where it's the same y and it's the same x, then that means we can just kind of get rid of this middle step and say, okay, if they're both equal to y, then they have to be equal to each other. Okay, so that's probably how I would do it. I will write it out a slightly more general way, right? So somewhat more generally, I can rewrite the first equation, y equals 3x minus 4. Then I see, okay, here's my variable y. Here's my variable y. Y is equal to -1/2 x plus 3. So I'm going to replace y, or substitute in for y, -1/2 x plus 3. And that will be equal to 3x minus 4. Now I get an equation that has variables on both sides, but it just have x. So I know how to solve this equation. Okay, I need to get the variables to one side of the equation, constants on the other, and solve for x. So that's what we're going to do now. Here I have 3x on the right-hand side of the equation and -1/2 x on the left-hand side. I want to only have variables on one side of the equation. So let's look at this -1/2 x, and I'm going to try to get rid of it. So if I have a negative 1/2 x, or like a minus 1/2 x is another way of thinking about it, how can I get rid of that negative 1/2 x? Right, I'm going to add positive 1/2 x. Okay, so I do that to both sides of the equation. On my left-hand side, negative 1/2 x plus positive 1/2 x. That goes away to 0, and I get 3 equals 3x plus 1/2 x is 3.5 x. I'm just going to make this in decimal form. That'll probably be a little bit easier. 3 plus 1/2 is 3.5 x, and then minus 4. At this point, I just have a two-step equation. X is currently being multiplied by 3.5, and then we're subtracting 4. We need to undo those things, working in the reverse order. So first, I'm going to undo that minus 4. How do I undo subtracting 4? Perfect. I'm going to add 4 to both sides of the equation. On the left-hand side, I will get 7. 3 plus 4 is 7. On the right, minus 4 plus 4 goes away, and I get 3.5x equals 7. And finally, x is currently being multiplied by 3.5. I'm going to undo that. I undo by dividing by 3.5, and 7.5, or 7 divided by 3.5 is 2. So I get x equals 2. Okay, now you're probably thinking, that was a lot of work. We have to be done. Unfortunately, that was a lot of work, and we're still not done. So we figure out that x equals 2. Wonderful. So that's giving me my x value, but we know the solution to a system of equation is not just the x value, it's also the y value that goes with that. It's the coordinate point. So now that I've figured out that x equals 2, I'm going to take that and plug that back in. We don't like that word. Substitute the value of that variable back into one of the original equations. So I could choose either one. Probably slightly better to pick this first one since there's no fractions. So this is y equals 3x minus 4. I just figured out that x is 2. Okay, so I'm going to replace x with 2 because, again, x equals 2. And then y equals 3 times 2 is 6. Minus 4, and I get y equals 2. Okay, so x equals 2, y equals 2. That means I want to then write my final solution as a coordinate point. The x value is 2, the y value is 2. The solution to this system of equations is the point 2, 2. Oh, look, that's what I got here. And then very briefly, we could also check our work. Right, so we kind of just checked it for the first one, but I can check my second equation. If instead of having x here, I have 2, I would get negative 1/2 times 2 is negative 1 plus 3. So then I get 2 equals 2. And that would be correct. Okay, so we know that this is the correct solution to the system. Awesome. All right, let's just take a look at one more example. Here we have 2x minus 3y equals negative 1, and then y equals x plus x minus 1. So this is my system of equations, and I want to solve it by substituting. So the first thing I want to do when I'm solving systems of equations is isolate one of the variables in one of the equations. So I want to have y equals something or x equals something. Okay, and looking at this, I'm in good shape there. I already have that y equals x minus 1. Great. Okay, so y equals x minus 1. Now what I'm going to do is I'm going to rewrite that other equation. 2x minus 3y equals negative 1. And I'm going to substitute in x minus 1 for y in parentheses. Whenever we substitute, we always do that in parentheses. So instead of having this y, I'm going to replace that in parentheses with x minus 1. Because again, y is equal to x minus 1. And then from there, I can just solve this equation. Okay, I have 2x minus 3, so we don't make any errors. We're going to turn this into adding a negative 3 times x minus 1 equals negative 1. I'm going to need to distribute because I have the parentheses. Negative 3 goes to x. Negative 3 times negative 1. Whenever we distribute, of course, we're multiplying. So then I get 2x plus negative 3 times x is negative 3x plus negative 3 times negative 1, be careful there, minus 1, we're adding a negative, so that becomes plus 3. And that equals negative 1. Okay, now I have some combined terms to combine, positive 2x and negative 3x. When I add those together, I get negative 1x plus 3 equals negative 1. Okay, then now I have x is being multiplied by negative 1, and then I'm adding 3. I need to undo. How do I undo adding 3? Subtracting 3. And on my left-hand side, I will get negative 1x equals negative 1 minus 3, that is negative 4. Thus, x is being multiplied by negative 1. We can undo that by dividing by negative 1, and we will get positive 4. Right? Awesome. Okay, but I shouldn't, that's my desire to box that in, but that's not actually the final answer. So we get x equals 4, great, but the solution to a system of equations is the xy value. So now that I know what x is equal to, I'm going to substitute 4 back into this original equation. Y equals x minus 1. 4 goes in the spot of x because x equals 4 there. And then I have 4 minus 1. So y equals 3. Thus, the final answer in the solution to the system of equation is 4, 3. The x value is 4 and the y value is 3. That will make both of these equations true. You can see if I make that x 4, I'm going to get 8 minus 3 times 3, that's 9, and 8 minus 9 is negative 1. And of course it works there too. Okay? If we were to graph these two lines, we would see that they intersect at the point 4, 3. But graphing this line is quite complicated, right? Because it's not in slope-intercept form, so we haven't really learned how to do that. We'd have to solve the equation for y to get it into slope-intercept form, and then at that point it's not really any easier. So algebra is going to be a good approach, and the substitution method is going to be a great approach when our equations are not in slope-intercept form, but one of the equations has one of the variables solved for, because then we can substitute it in easily. Okay? Awesome, great job everyone.